kind of a turn here, solution concentration. So think about what happens if you sprinkle salt, just table salt, into water. You stir it up. It seems to disappear, doesn't it? Is it still in there? Yeah, if you taste the water, it's very obvious there's salt in it. So what it does is it dissolves and forms a homogeneous mixture of salt and water. A homogeneous mixture is also called a solution. Solutions have two basic parts, the solvent and the solute. The simplest way to identify which is that the solvent is generally present in greater amount. There's more of the solvent than of the solute. The solute is present in lesser amount. That designation doesn't always work out. Another way to think about it is that the solvent keeps its physical state. The solute may change its physical state. And you can have more than one solute. Because you could put salt in that water, and you could pour some sugar in there too, right? And the sugar would also dissolve. And so now you have sugar and salt dissolved in the water. But there's more water present than either the sugar or the salt. The sugar and salt were solids to start out with, and now they're aqueous. They've changed their state. The liquid water was liquid before, and it's still liquid. So the solute is what's dissolved in the solvent. It can be a little confusing at times. So solutions are mixtures. The composition can vary. These are not pure compounds with a fixed proportion. Pure substances have constant composition, always the same ratio. In a mixture, it can vary. So we need to have some method of describing the relative amounts of the solute and the solvent. Pure substances, we just give them a name because they're always the same. Water is always the same. It's always 2 hydrogens and 1 oxygen, same ratio. Salt water, you could have a little sprinkle of salt in the water. You could have half a cup of salt in the water, right? We have some qualitative descriptions for solutions. These are not involving numbers, they're just the quality. So we can talk about dilute and concentrated solutions. These are just relative terms. They have no absolute meaning. So a dilute solution is going to have a small amount of solute, and a concentrated solution is going to have a large amount. Well, who decides which is large and which is small? Well, if you have 2 solutions and one is higher than the other, then you've got the concentrated and the dilute. If you're just looking at one solution and you're trying to decide, is this concentrated or dilute, then it becomes a little more difficult. But, of course, we need some quantitative descriptions. So the one that we use the most in chemistry is called molarity. Molarity is abbreviated with a capital M. Sometimes I see students using a lowercase m. Lowercase m is meter, okay? And MOL is mole, right? So we have our set abbreviations, and we're very rigid in how we use them so that we don't confuse each other. Molarity is the amount of solute in moles divided by the volume of the whole solution in liters. So in equation form, molarity equals moles divided by liters. It's moles of the solute divided by the volume of the whole solution. The volume of the whole solution is a little different than the volume of the solvent. Think about this. Think about taking a glass of water, a drinking glass at home, fill it to the brim with water. Now take 1/4 of a cup of salt and pour it into the glass. What's going to happen? Some water is going to spill out, right? Because the salt occupies some volume. The volume of a solution relative to the volume of the individual ingredients is not something that's easy to predict. And so we always just measure the volume of the total solution. Here's an example, illustration, I should say, of how you would prepare a solution of a known concentration. You are going to be doing something very similar to this in lab today. The masses and the size of the glassware is going to be different, but you're actually going to be using sodium chloride. So this is a 1 molar sodium chloride solution. So that means it has 1 mole of sodium chloride in 1 liter of solution. So if we have a 1 liter container, we're going to add 1 mole of sodium chloride. Well, you have to convert that to grams so you can weigh it on the balance. That would be 58.44 grams. We're going to measure that mass, and we're going to transfer it into the glassware. This is a volumetric flask. It is one of the more precise glasswares, and it's designed to contain 1.00 liters. When transferring solids, it's often helpful to use a funnel to make sure that you're not spilling. Next, you're going to add some water. Partially fill this and swirl it around. You may want to put the stopper on and shake it. You want to get all that solid dissolved in the water before you fill it up. Once you get the liquid up into the neck of this, it becomes much harder to mix. So you want it all dissolved before you start really filling it up. Then you're going to add water. There will be an etched or a printed line on the neck. Some of them might be near the top, some of them might be lower, but each of them has been marked individually where the 1 liter mark is. So you fill till the bottom of the meniscus is at the line. Then you stopper the flask, and you need to invert it and let the bubble go up and then turn it right side up again. You need to do that like 20 times to make sure that it's thoroughly mixed. And then you have a 1 molar sodium chloride solution. Any questions? The neck here is very skinny because then 1 drop of water is going to have a noticeable difference in the level. And so we can measure more precisely and more accurately what the volume is compared to something big like a beaker where it's really wide. And you can add a little bit of water and you don't necessarily see much of a difference. And so that's why the glassware is shaped this way. Questions? Let's calculate the molarity of a solution made by adding 4.5 grams of sodium nitrate to a flask and dissolving it with water to create a total volume of 2.50 liters. Calculate the molarity. So we need to remember what molarity equals. Molarity equals moles of solute divided by liter of solution. Did they give us either of those? They didn't give us moles, but they gave us the volume of the solution, right? So we got 2.50 liters down here. That's the volume of the solution. We're going to have to calculate the moles. So we've got 45.4 grams of sodium nitrate. And we need moles. So we want to convert this to moles of sodium nitrate. So we're going to have grams of sodium nitrate down here. And then our units are going to work out. We have to calculate the molar mass. So for sodium nitrate, we've got 1 sodium, 22.99, plus 1 nitrogen, 14.01, plus 3 oxygens. It's one of those funny ones that comes up 85. Does that only have 2 sig figs? Or is it an exact number because I got a whole number on my calculator? Well, where did this number come from? It came from adding these together, right? It should have 2 decimal places. It should have 4 significant figures. So we really should put those in there. The calculator doesn't put in zeros after decimal points. So it's 85 grams per mole. It's not going to matter in your calculation, but if you were checking your sig figs, it could throw you off. So I'm getting a moles here of 0.534. Based on my starting mass, I should have 3 significant figures. I don't want to round it off yet, though. I want to carry like 2 extra ones. So I'm going to go 1, 2, because it was 1176. So that's my moles, and then I'm going to plug that into this equation. So I take the moles, I divide by the liters, and now this is my final answer. I can round this, and I get 0.214 molar. That can also be written 0.214 moles per liter. I underline my capital M's because I don't like to take the time to make them very pointy and make my lowercase m's very curvy. And then the size fluctuates a little bit, and by underlining that capital M, that says this is a capital M, not to be confused with meters. Any questions? Yes?
Is the molarity always going to be less than 1?
No. The molarity is not always going to be less than 1. It can definitely be greater.
How is that possible?
Some compounds are very soluble in water, like sodium chloride.
Like, so they'll dissolve in a greater amount than the original amount of the base?
Well, there are solutions where the mass of the solute is actually greater than the mass of the solvent.
So that can
But here we're looking at moles per liter. Sodium chloride is 58 grams per mole. So if you had 1 mole, it'd be 58 grams, right? The 1 liter of water approximately would be 1,000 grams. And so even a 1 molar solution, you don't have equal amounts of water and liquid.
But is it possible to dissolve 1,000 grams of salt in 1,000 grams of water?
I don't know if it's possible for sodium chloride, but there are substances where it is possible. Yeah. So molarity makes a really nice conversion factor. We've used molar mass a lot as a conversion factor. And when we have solids that we're weighing on the balance, molar mass is a great conversion factor. When we have solutions, we use the molarity as the conversion factor. That's the relationship between volume of solution and moles of substance that we're interested in. We take those solutions and we measure their volumes, and then we can identify how many moles we have. So the example here is a 0.500 molar NaCl solution. Molar means moles per liter, so that would be 0.5 moles per liter of solution. So that's a conversion factor. That would convert from liters of solution to moles. Or we can flip it upside down, 1 liter per 0.5 moles of sodium chloride, and convert from moles of solute to liters of solution. Let's do an example. How many grams of sucrose are in 1.55 liters of 0.758 molar sucrose solution? Well, let's just write some stuff down. I've got 1.55 liters, and I've got 0.758 capital M. The capital M for molarity is very convenient on the computer. because it's not a fraction. When you're writing, though, you can write vertical fractions just as easily as you can write regular letters. So when you write that down, write it as the vertical fraction that it is, moles per liter. Otherwise, you may overlook that it's actually a fraction of units, moles per liter. When we write it this way and look at it, we think, oh, that's a potential conversion factor right there. This volume, that's not a conversion factor. We're trying to find grams of sucrose. So we're trying to find grams. And I'm approaching this just as a dimensional analysis problem. We have to figure out which one of these to start with and then make a path to get from that over to grams. So what I've told you before is just look at the unit. This is liter, this is moles per liter. This is probably a conversion factor you're going to need. We're going to start with liters. So we're going to start with liters. And from liters, we can use this conversion factor to get to what? Moles. So we can get to moles. Could we go from moles to grams? Sure, we've done that a bunch of times now. So there's my path. There's no formula or equation you have to memorize. It's all in the units. 1.55 liters, and I want moles here, and then liters will be on the denominator, and then here I want grams on top and moles on the bottom. I didn't write grams or moles of what. I could, I don't absolutely have to here, because we're just talking about one substance. With the chemical reactions, we have one thing turning into another substance, and so we have to identify them. Here, you could skip that. So the relationship between moles and liters is this molarity that was given. 0.758 moles per liter. Molar mass, we have to calculate. They gave us the formula. 12 carbons times 12.01, 22 hydrogens, 1.008. Sucrose is table sugar, by the way. And 11 oxygens. Calculator went to sleep. .296 grams per mole. If I'm thinking about sig figs, you could argue it either way, that this has 4 significant figures or 2 decimal places. Either way, it's not going to limit my final answer. So then I've got 1.55 times 0.758 times 342.296. And my final answer should have 3 significant figures because the volume and the molarity both had 3. And so this is going to come out to 402 grams of sugar. Any questions? Solution dilution. We often keep solutions back in the stockroom in more concentrated form, kind of like they sell concentrated orange juice at the grocery store, because it's convenient. And then you take the solution that's more concentrated and you can dilute it by adding solvent and make it pretty much anything you need. When we dilute a solution, we're just adding more solvent. The amount of solute doesn't change. You think about making orange juice from concentrated frozen orange juice. You take that can and you take a pitcher, right? And you squeeze all the orange goodness out of the can into the pitcher. And then you take the little can to the sink and you fill it up with water and you pour it in the pitcher. Does that change how much orange stuff is in your pitcher? No. And then you do it again. Same amount of orange stuff. All we're doing is we're adding water, right? Same amount of orange goodness. But now it's becoming more diluted. And we're going to dilute it so that it's at a level that's similar to fresh squeezed orange juice and it tastes good. You could keep adding water and make it really watery and not so nice. So when we're diluting chemical solutions, it's the same idea. We're just adding water. The amount of solute stays the same. So because of this, we have this relationship. The molarity of the one solution times its volume is equal to the molarity of the second solution times its volume. So let's look at an example. You're going to be doing this in lab today too. Diluting a solution. So here they've measured 0.15 liters of a 10 molar stock solution. So this 0.15 liters, 0.15 liters times the concentration of 10 moles per liter, the liters cancel out, and that contains 1.5 moles of the solute, the stuff that's dissolved in there. We're going to pour it into this big flask, the pitcher. So this is like the orange juice concentrate. We're putting it in the pitcher, and we're adding water. Now the volume has increased. The volume's changed. The volume went up. The concentration went down. But they are proportional. If we take the new volume, now it's 3 liters, times the new concentration, 0.5 moles per liter. The liters cancel out. We get 1.5 moles. The moles of solute didn't change. That's why that equation works. Okay, so you can call the concentrated one number 1, or you can call the dilute one number 1. It doesn't matter, just keep them straight, what you're calling 1 and 2. Let's do an example. To what volume in milliliters should you dilute 100 milliliters of a 5.00 molar calcium chloride solution to obtain a 0.750 molar calcium chloride solution? There's a typo here, so I have to fix that. There, that's better. We have 2 solutions, and they actually use the word dilute, so that's a clue. We're going to need that M1V1 equals M2V2 equation. The molarity of the first one times the volume of the first one equals the molarity of the second one times the volume of the second one. Does the volume have to be changed to liters? We're going to see. You can, but we'll find out in this one it doesn't actually have to. So let's say that the first solution that shows up in the problem is going to be the first solution. So we've got 100 milliliters, so that's a volume. Volume 1 is 100 milliliters of 5.00 molar. So that's the concentration. And molar is moles per liter. That's the first solution. Then 0.750, that's a molarity. That's the other solution, so that's going to be molarity 2, 0.7500 moles per liter. And what is volume 2? That's what we have to find out. They're not going to give you all 4 of them. They're going to give you 3 and make you find the other one. So we are trying to solve this equation for V2. So we need to rearrange the equation. So here I have molarity 2 times volume 2. I want to move molarity 2 to the other side. I want to get V2 all by itself. So I can do that by dividing by M2, because M2 over M2 is 1, poof, goes away. If I do it to one side, I have to do it to the other side so that the equation is still equal. So I'm going to divide by M2 over here. So I'm going to rewrite that. I'm going to switch to blue. V2 equals M1 V1 over M2. Everybody okay with that? I have my numbers up here. I can plug them into the equation. So I've got M1 is 5.00 moles per liter. The question earlier was, do we have to convert to liters? I'm being very careful here to put all my units in, and then we'll see what we need to do. So there's my molarity 1, and my volume 1 is 100 milliliters. And I'm dividing by molarity 2, 0.750 moles per liter. Before we do the math, let's look at the units. What happens to the units? They all cancel out except the milliliters. So moles and moles cancel, liters and liters cancel. So in this situation, I did not have to convert to liters and then back to milliliters at the end. If you do that correctly, you're going to get the same answer. And so I'm not saying that you can't, but in this situation, we didn't have to. So now I've got 5 times 100 divided by 0.75 equals, oh, there's a scary number, 6.66666666. Just keeps going. How many sig figs should we have? 3, right? So that's going to be 667, and what's the unit? Milliliters. On these dilution equations, it's really easy to get 1s and 2s flipped, especially if you have any sort of tracking issues. So always ask yourself, does this make sense? So we're taking 100 milliliters and diluting it. Is the volume going to get bigger or smaller?
Bigger.
It's going to get bigger. When you take the orange juice concentrate and you dilute it, you end up with a larger volume. My volume went in the right direction, and so that's a good sign. It doesn't prove anything, but if it got smaller, then I'd need to go back and see what I did wrong. Any questions?